Welcome back to the lectures in chemistry and the introduction to molecular spectroscopy. I just finished in the last lecture with a very simple and a quick definition of what is known as a tensor, and I think it is important for you to understand even in a rudimentary form the idea of a tensor, because the molecular spectroscopic quantities that you deal with, some of them have components from the higher rank tensors and some of them are vectors. The dipole moment is a vector, for example. The polarizability is a second rank tensor, as I told you earlier. The hyperpolarizability, which is often measured for nonlinear spectroscopic systems, is a third rank tensor, and then there are higher rank tensorial properties which are often studied. In the introductory course we do not have to go as far as that, but in even the study of an elementary account of Raman spectroscopy, it is important for us to have an appreciation of the idea of tensor. Now, if you remember, we will start with the polarizability tensor first in this lecture, and if there is enough time I will also introduce you to the idea of moment of inertia being the second rank tensor and what the components are. Okay. So, first let us write the relation that we left in between, namely the induced dipole moment mu, which is a vector in terms of a second rank tensor alpha which changes the electric field to give you the induced dipole moment. What exactly is this picture? Suppose you have electric fields in this direction and you have a molecule, for example say NO. Let us consider NO to be in this direction. Suppose the field is in this direction, is moving in this direction, field is pointing in this direction, and the NO molecule is sitting in a perpendicular direction. You know that the bonding electron of the NO is between the two, nitrogen and oxygen. The electron density is concentrated there, and the electron density will try to adjust itself with the positive side of the electric field and the negative side of the electric field in such a way that the molecule will have a slight orientation, and there may be a slight deformation of the electron density if the fields are very large. To what extent the molecule is able to polarize itself, to adjust itself to the external field and undergo simple changes in its geometry, that number is given by the number is by this quantity in a certain form. If the molecule is like say HCN, it has the bending vibrational modes, it has stretching vibrational modes, it has what is also known as the symmetrical, in the sense both the hydrogen and nitrogen atom going one way and then the hydrogen and nitrogen atom going in the opposite directions and so on. That is a normal motion. Now, if you put such a molecule which is undergoing vibration in an electric field, the electric field may induce an additional dipole moment, and that induced dipole moment is directly a function of the property of the electric field. And remember, I put a double arrow on top of it instead of writing it simply as alpha E, because it is possible that the induced dipole moment of say NO in the field, in the presence of the field, see NO itself is undergoing some vibrations. So, if I have to write N double bond O, there is a mu, and now if this molecule is in the electric field E, there may be additional induced dipole moment, and that may not be in the direction of the electric field, and therefore you have this quantity called the second rank tensor. Exactly how do we write? This is a vector, therefore you have three components: mu induced X, then mu induced Y, and mu induced Z in the axis system, which defines also the electric field. If the electric field is in the Z direction, then you know in a plane perpendicular to the Z direction is where the x and y axis are, and with respect to that axis system, the mu induced is a vector, therefore it has 3 coordinates, and if you put this together, and the electric field itself has 3 components Ex, Ey and Ez in an arbitrary direction, and suppose we would put this as 3 components, then alpha is given by a 3 by 3 matrix, and the components of alpha, the indices that you see here, it's not 1 1 1 2 1 3, but they are related to the direction on this side as well as the direction of the component on this side, which is the effect. This is the cause, this is the effect, and the alpha connects the cause to the effect, and therefore the directions of the cause and the effect are written as xx. Okay. If you write all of these as capitals, x, y, z, then alpha xx times Ex, meaning that this is the component which tells you that the x component of the induced dipole moment with respect to the x component of the electric field, and likewise alpha xy, alpha xz, and alpha yx, alpha yy, alpha yz, alpha zx, alpha zy, alpha zz. What does this mean? This essentially means that the induced x component dipole moment mu induced x is given by the effect of the Ex alpha xx, the Ey alpha yy, and the Ez alpha xy and alpha xz. Okay. This relation, that the induced dipole moment is actually a function of all the 3 components of the applied electric field, and the respective coefficients connect them to give you the total value. This is the tensorial relation. What about mu induced y? This is capital X, this is capital Y. It's alpha yx Ex plus alpha yy Ey plus alpha yz Ez, and likewise mu induced Z is alpha zx Ex plus alpha zy Ey plus alpha zz Ez. Therefore, you have got these 9 components xx, xy all the way down to zz. These 9 components in the definition of the tensor that I gave you in the last lecture, these 9 components behave under coordinate rotation the same way the unit dyads, the xx, xy, xz, there are 9 unit dyads. These 9 dyads. How do they transform under coordinate rotation? In the same way, these quantities transform, and therefore they become the quantities of a second rank, the components of a second rank tensor. Okay. Now, one interesting thing is the fundamental property of the microscopic system appears to tell us that the xy and yx, see the connection between them. They are equal. First of all, that's the result. That's the result that comes from the microscopic considerations. First of all, you see the xy is a component due to the y component of the electric field inducing a change in the x, that is a mu induced dipole moment, but an x component. That connects, xy connects Ey to mu induced x. Yx connects the x component of the electric field leading to a y component of the mu induced. They are switched around. There are beautiful principles known as reciprocity relations in basic physics. I don't want to say much about them, but in this case the property is that such quantities which are connected with the reversal of directions of the electric field and the outcome, they are both equal by geometrical as well as physical considerations. In the same way, alpha xz, and let me write that, alpha xz and alpha zx are identical, alpha yz and alpha zy are identical. Therefore, what we have here is not 9 independent components, but only 6 independent components, because all these off diagonal components, this is the diagonal, these are the 3 off diagonal components, this is the same as alpha xy, this is the same as alpha xz, diagonally opposite is alpha yz. So what you have is essentially xx, xyy, zz, xy, xz, yz. So 6 independent components for the polarizability tensor. That's one more little step. This is with respect to the coordinate system, x, y, z. Okay. But and the matrix that we have here, the alpha xx, alpha xy, alpha xz, alpha xy, alpha yy, alpha yz, alpha xz, alpha yz, alpha zz. This matrix is called the second rank tensor matrix of alpha, and it is a symmetric matrix. Symmetric matrices have the property that they can be diagonalized to give only what are known as diagonal elements. That is, this can be diagonalized to give the final form of some alpha xx prime, alpha prime, alpha yy prime. This is not the same as that, but it comes after diagonalizing this matrix. You get alpha zz prime with zeros everywhere else. Okay. This property of transformation defines 3 angles or 3 real coordinates, and therefore of the 6 quantity that you have, 6 independent quantities that you have, you reduce them to only 3 independent quantities by removing the 3 quantities constraints as coordinates, as rotation axis or rotation angles. Therefore, what is left over is 3. But there is one more property. Such a diagonalization also ensures that the trace of the matrix alpha xx plus alpha yy plus alpha zz is always equal to alpha prime xx plus alpha prime yy plus alpha prime zz. The trace of the matrix, the trace is the sum of the diagonal elements of the matrix, the sum of the diagonal elements of the matrix. The trace of the matrix is invariant to the process of diagonalization. In this case, this is a similarity transformation, and this being a real matrix and symmetric matrix, this similarity transformation is also known as an orthogonal transformation. Therefore, what happens is that not only do we have 6 quantities come down to what is called 3 quantities with respect to some new axis system. Okay. So better would be to write this as x prime, y prime, z prime to indicate that we have a new axis system. This is some fixed axis system, and in the new axis system we have only 3 quantities, and therefore accordingly this will also be x prime, y prime, and z prime. This axis system is called the principal axis system. Therefore, our idea in doing experiments is to find that particular axis system known as the principal axis system, in which we have only 3 measurable quantities x, y, z, z, but they are connected by the fact that this is a constant, because if you don't choose the principal axis system but some other axis system, you still have the relation that the sum of the 3 is the same as the sum of the 3 in that axis system. So there is a constraint that there is a constant. The constant is the sum of the 3. Therefore, we have 3 independent quantities, but with one constraint, 3 quantities with one constraint. Therefore, finally we have only 2 independent quantities. These are called the polarizability parallel and polarizability perpendicular, that we will talk about in Raman spectroscopy in the next lecture. Therefore, what you see here is the property of what is known as the polarizability as a tensor, and later the tensor being transformed to something called a principal system, and then removing the constancy of the sum of the 3 components, we see that there are 2 independent polarizability components that we can measure, and Raman spectroscopy gives beautiful results about the experimental. From the experiment, it gives you beautiful information about the molecular polarizability. We will continue now with the Raman spectroscopy in the next lecture. Thank you.